quantum computing, which is also our last lecture. Unfortunately, that time went by quickly. So what we will talk about today is adiabatic quantum computing and quantum annealing, which is a different architecture of quantum computers than the one that we learned about before, namely gate model quantum computers. As you remember, a gate model quantum computer operates by stacking together gates, or you stack together gates, and can so represent any arbitrarily complex problem or any arbitrary algorithm on that quantum computer and run through it. Doesn't always make sense because for some problems we already have classical computers and they solve them fairly efficiently. We want to have a look at those problems that a classical computer cannot solve efficiently or cannot solve at all. Right now we're in this regime with adiabatic quantum computers where we talk about problems that classical computers cannot solve efficiently. They still can solve it, but it may make more sense to use a quantum annealing system. They're bigger than than gate model chips. So they're more practically useful these days. They come with a limitation though, and this is that you can only use them to solve optimization problems. But luckily it turns out that a lot of the problems that we deal with in our everyday world are optimization problems. Think about training a neural network, how you propagate back the error of a neural network and adapt the weights. This is an optimization problem. So you want to find the minimum value configuration. You want to minimize the error in that case. Then there are, of course, all optimization problems that we know of that are optimization problems by nature, like traffic flow optimization, minimizing or optimizing flight schedules. That's something we can have a look at. Also more complex ones when it comes to finding the ground state of a molecule. This is also a minimum value problem. So what you want to do is find the lowest energy configuration of a system and of a molecule in that case. And you want to do that because that's the best approximation to the real wave function. And this is also something where you can use a quantum annealing system because as I said, it's designed to solve optimization problems. How it does that, we will learn today. But the whole idea behind it is that you have or use the properties of physics again. So any physical system will tend towards the energy minimum over time. And this is what annealing systems do. They just do their thing, end up in the minimum. And if I understand that process well enough, and if I have an idea of how I can inject my problem, and that, so we call it Hamiltonian. So how I can inject my problem Hamiltonian, the energy function, then I can solve it, and I can find when I formulate it correctly, I can find a minimum value configuration of, let's say, traffic that minimizes traffic jams. This architecture has also been conceived almost 2 decades ago already, but only over the last, I would say, 5-6 years, we have seen systems that are practically useful on the market. Right now, we're dealing with about 2,000 qubits. We can expect about 5,000 by the end of this year. So when it comes to D-Wave systems, so I've heard about D-Wave as a manufacturer of quantum annealing systems. I don't know of any other company that, so I know a couple that work on quantum annealing, but no other company that is that far when it comes to developing quantum annealing systems. And so remember, it's still a quantum computer. It uses all the quantum effects for computation. However, it's limited to solving one problem, and this is optimization problem. So it's quantum annealing. And so this is why it's always criticized, or very often criticized. I think not so much anymore, because people see that it is useful and can be used to solve practical problems. There was even a recent proof where people showed that you have quantum advantage. So where you have a problem that is solved on a quantum annealer that a classical algorithm can't beat. So a classical algorithm incorporates any system that's underneath. So anytime I say classical algorithm, I also mean the hardware and the maximum performance that you can get out of any hardware, okay? Anyway, so one thing we also want to have a look at and keep in mind here at the quantum annealing systems is the Pauli matrices. They are always important in quantum computing. Just remember these 4 matrices, so actually the 3 and the identity. So the identity transformation, as you remember, it just leaves a state as it is. You want to apply that identity transformation, for example, when you have a 2-qubit operation that manipulates only 1 qubit and you want to leave one alone, and you have identity. So then we have X, which is a not transformation, so a negation. It makes 1 to 0 and 0 to 1. We have Z, which changes the relative phase over superposition in the standard basis. So a standard basis is the basis 0 and 1, and then maybe you have superposition state, which says 1 over the square root of 2 times 0 plus 1. So it will make 0 minus 1 out of that. So it changes the relative phase. The relative phase change matters. It is a different state then. If you have a global phase, remember that too. Phase change doesn't matter. If I have plus 1 or minus 1, doesn't matter. It's the same physical state. So if it's just 1, not a superposition state, okay? Then I have Y, which is a combination of Z and X, so a negation and phase change in 1. So we want to keep that in mind. Specifically, we will use X and Z for what we're going to do right now. We also want to remember eigenvectors and eigenvalues. So an eigenvector, so the formal definition says, is the eigenvector of a square matrix A is a non-zero vector V such that multiplying A by V yields a constant multiple of V. So what does that mean? That means if I have a vector and I apply a matrix to that vector, the only thing that changes is it's not the direction, it just is a multiple. It makes it, it stretches it. But it doesn't change direction at all. So, which is the same as applying a scalar multiplication to that vector. So, and if you take that scalar, that's the eigenvalue. If you take that vector, that's the eigenvector of that matrix A, okay? So that's the jargon that we use here. Summing up, so we learned about how we can get to eigenvectors and eigenvalues. It's not too difficult, especially when it comes to 2D matrices only. But let's look at the Z matrix here. So if I apply the phase change matrix to the state 0 in that case, then what happens is it remains 0, right? But if I apply it to the state 1, it changes the phase of the state 1. So to plus 1, it becomes minus 1. Okay, that's what happens here. And the eigenvalues, so each of the Pauli matrices have two eigenvalues, plus and minus 1. And this is what we see here in that multiplication below. So we have the eigenvectors, 0, 1, these are the basis vectors that are the eigenvectors of these matrices, and then the eigenvectors, which is my eigenvalues, which is minus 1 and 1 for these matrices, for all of the Pauli matrices. So the X matrix has the same eigenvalues, but a different pair of eigenstates, which can also form an alternative pair of basis states to 0 and 1. So these are also orthogonal to each other, but we could say in this vector, instead of 1, 0 or 0, 1, we create superposition states that are orthogonal to each other. So in that case, 1 over the square root of 2 and 1 over the square root of 2. So X plus would mean 1 over the square root of 2 times, so let me write that down. It's the state 1 over the square root of 2 plus 1. This is X plus, and we have X minus, which is 1 over the square root of 2, 0 minus 1. And again, if you apply the eigenvectors to that, you can see the very same result. The eigenvalues, there's a very same result. That generalizes, of course, to multiple qubits and superposition. So remember, we talked about two-dimensional qubit space being four-dimensional vector space. That's, again, the summary that we see here. Nothing new, it's just a recap. So if you want to take more time to go over that, please feel free to do so. But I think it's still fresh, so we don't need to write all that stuff down again. We also remember entanglement. That's also important in a quantum annealing system. So you remember entanglement, if you compare it to everything that we have classically, then the most suitable thing is correlation. But it's stronger than usual correlation, stronger than classical correlation, entanglement. Because if you look at maximally entangled states, such as the one that we have here, then what you see is that you cannot separate these into single states by, or decompose it into tensor product of 2D states, so or 2D vectors. It's not possible. So we have this 4D vector here, but you cannot decompose it. And you see here in these slides why it's not possible, because if it was possible, or if you try it out, then either of these must be 0 as well, and that doesn't work. So what that means is anytime you have a system that you cannot decompose to a tensor product of two smaller systems, then anytime you do something to one part of the system, it also affects the other part of the system. Okay, there is no way around that. That's just what it is. Think about it classically as stronger than normal correlation. Entanglement in terms of practical problems can mean, so if we talk about traffic flow optimization, I always have an easier time talking about problems or describing things with problems. So if you talk about traffic flow optimization, take 5 vehicles or take 10 vehicles and move them to another place. Fine, you solve the traffic problem here, but I also want to see what happens to the other vehicles, so the target area. And it cannot be that my traffic situation gets worse over there. And in a quantum annealing system, we express the effect that one vehicle has on another, or one or n vehicles have on n other vehicles via entanglement. So that's how we do it. We remember the gate model computer. So it's just that as an example algorithm that we see here. We start with an input register of a queue of n qubits, which is operated on by gates or circuits in parallel. And we initialize Q to some known state, like all zeros or all ones, and apply the circuit to induce a state transformation. We talk about the evolution of the system over time. And then we measure Q, which causes a probabilistic collapse. So even if you do everything right, it may happen that you end up with a wrong solution, because there's still a probability that you get a solution, even though if this probability is very small, there's still a chance that you can end up with a solution that you don't want. And this is also the case in quantum annealing systems. We don't read out from the chip only once, we read out maybe 1,000 times. And 800 times, hopefully we will get, we will get the identical solution. Maybe 200 times we'll get a solution that is just random. So we will not take any of these random solutions. We will take the ones, the 800 identical ones, and say that is the solution to my problem. For quantum dynamical systems in general, so we say we have n qubits in a register Q that are particles in the quantum dynamical system evolving over time according to certain forces acting on it. If we work with magnetic qubits, then that means we interact with magnetic fields. So these are the forces that are acting on it to manipulate states or induce state transformation. The superposition of Q is at, as we have seen before, is at T is phi or psi of T. So and at any T, the forces are characterized by time-varying Hamiltonian. So remember the Schrödinger equation, which says the Hamiltonian applied to a system gives you the energy of a system. So basically it says the Hamiltonian applied to a system equals the energy of a system, and this is your scalar, so this is an eigenvalue problem. Again, this is a matrix. So in these forces, so anything that interacts with your system can be characterized by time-varying Hamiltonian, which is an n by n Hermitian matrix. We learned what Hermitian matrices are. And time varying means it changes over time, because we want to find out our solution to a problem, right? And before we now look at a very simple example problem, we want to talk about the components that we need into an adiabatic quantum computing algorithm. We need an initial Hamiltonian. So this is the starting configuration. It's a very similar way of thinking than we have with our gate model. So instead of defining an input register with the zeros and ones, we have now an initial Hamiltonian, which we understand well, which is the ground state of the system. That's easy to find out. So we want to start in the ground state of the system. That's where we start. So whatever that quantum annealing system is, that ground state we need to understand, and that's how we start. And we want to have a final Hamiltonian encoding the objective function. So what is the problem that I want to solve? And is it possible that so it is possible, before I answer my own question, it's possible to express that as a matrix, and this objective function, so that the ground state Q that we want to find is a solution to the problem. So it's an eigenstate of HF, the final Hamiltonian, having minimal eigenvalue. It's the optimal solution. The adiabatic evolution path, so the system also does its thing over time, so it evolves. Adiabatic solution path is a function s of t decreasing from 1 to 0 as t approaches tf. 0 goes to tf, so it's the final time. So as long as the system can maintain a state, or as long as the adiabatic cycle is. So remember, this is also another thing. With gate model and quantum annealing systems, we have this challenge that we cannot always we cannot maintain a superposition of states as long as we want to, because interacting with the system will cause a collapse. So it will result in decoherence of that superposition and leave you with that one probabilistic final result. So all the information of a superposition, as you remember, is lost. And so therefore, we also must be careful here. Sometimes even here we create iterative algorithms. So take the output of one and feed it in again. It's also something we may want to consider if the time isn't enough, or if the size of the chip isn't big enough. So there are decomposition algorithms. So sometimes you have a matrix that is bigger than what a chip can take, but then still for some problems like traffic flow, no problem, I can decompose. I can take that part of the city and just make the whole city a big matrix, but cut out that chunk, and then take the borders for the next matrix and cut out that chunk and feed that in and solve that. So in a circular fashion, you could say. And then there are other problems like simulating molecules. So where you have electrons interacting with electrons via the Coulomb repulsion interaction. You have electrons being attracted by the nuclei. You have nuclei that have repulsion to each other. And that's all complex. So if you have, and you all need to consider all interactions all the time. I cannot cut off one nuclei with the electrons and calculate that and then calculate the other one. It's not possible. I have to make sure that this problem stays intact. So remains in that big matrix. So this is a problem, an example for a problem that you cannot cut apart or cut piece into smaller instances. So remember that function here, s of t is 1. So let's just write that down. Let's say s of t is 1 minus t by tf. Okay, so that's the current time we're at. This is the final time. All right. Then we will look at this adiabatic quantum algorithm as a whole. So you see, remember s of t, that function here, that you see on the left side. So the Hamiltonian, the overall Hamiltonian of the system at time t is given by the initial Hamiltonian times s of t plus 1 minus s of t of the final Hamiltonian. And if you look at that, that tells you something. That tells you as time progresses, the initial Hamiltonian becomes less important and the final Hamiltonian becomes more important. It gets more weight. And that is what an adiabatic quantum computer does. So over time, you want to make sure that the system remains in the ground state or close to the ground state, because that's where it starts. And then when you induce your problem Hamiltonian, the final Hamiltonian, your objective function, however you want to call it, you want to make sure that the system maintains in the ground state. And just, you can imagine it somehow as this final Hamiltonian as a superfluid going over hills and valleys, and it adapts. So in the end, you will end up with the optimal solution extracted from your objective function, or how you formulated that, but the system maintains the ground state. So that's why you have to have this evolution path here. Well, maybe it becomes a little clearer when we look at an example problem. The problem that I have here is the 2-bit disagree problem, very simple one. The output should be 0, 1 or 1, 0, but not 0, 0 or 1, 1. So that means the bits have to disagree. You have 2 bits, can be generalized to bigger systems, of course, but you have 2 bits in that case, and you want to make sure that the 2-bit values disagree. That's it. So the objective functions on bits x is given by x1 times x2 or x1, x2. It's given by this f disagree that we have here. So Very simple. 0 is the output if they disagree, 1 if otherwise, if they agree. So what you see here is we want to have the solutions to a problem that have, so we formulate it such that 0, the smaller value, is the solution, is associated with possible solutions to my problem. So with the 0, 1 or 1, 0, and 1 otherwise. So 0 is smaller than 1, so that makes it an optimization problem that I can formulate as a matrix. So the final Hamiltonian, so remember the Z matrices that we just had a look at before, Z matrix, is given by the disagree or final, how do you call it, 1 plus Z of the first one, Z of the second one over 2. For building n times m Hamiltonians, that generalizes, of course, but so with a tensor product again. But let's have a look at the specific example. So for 0, 0, what does it do? We have, for the first one, the state 0, you remember, that's here. If you apply the Z matrix to that state, to that superposition state here, it doesn't do anything to that one here. It changes the phase of 1. Since we have 0 here, it leaves that alone. So which means it's 1 plus 1 times 1. So because I have 2 times 0, that I have a positive phase here, which is 2 over 2 is 1. And let's look at the second one. Here I have a different situation because here I have a 1 with the second qubit. So again, if the first qubit is a positive phase, so therefore Z makes it just plus 1 times 0, but this one here is plus 1 in the first, in the beginning. But then when I apply the Z transformation, it becomes, you get minus 1, okay? So that means 1 plus 1 times minus 1 over 2, which is 0. Same for the second disagree and the same number, so the same 1 as a result for 1, 1. So that was the final Hamiltonian. But now let's look at the initial Hamiltonian. So how do we start that system? And here, remember these two states here that we looked at. For each of the qubits, we apply this transformation. So we start with the X matrix for each qubit. Okay, so and that gives us the result here. If you do the calculation, and it gives you 0 for x plus plus, 1 for x and x minus, x plus and minus, and 1 for x minus and x plus, of course, and for both negative, it gives you a 2. So that's the initial Hamiltonian that we kick our system off. So and then remember, we have the time decreasing, so this S of t function, making the final Hamiltonian more important over time. And then how we run it is acquire the 2 qubits that we have with the states described at phi t at time t, apply the energies according to h of t for t as 0 approaches the final time. And then at the end of the computation, Q is in a low energy superposition state. And then we measure in the standard basis. The standard basis is 0 or 1. And then we have a probabilistic collapse into a binary string. Okay? That's how we solve the problem. That's the result that we get. And yeah, that wasn't too complicated, right? So that's how adiabatic quantum computing works. And let's look at quantum annealing now. This is the specific version implementation that D-Wave implement. So the quantum annealing system that is available out there that you will most likely use if you look into quantum computing, use first for practical problems. But the initial, so let's look at simulated annealing first, which is a classical algorithm. So, and it's derived from the cooling of metal. So if you have a metal, you heat it up and it's glowing, then you know heat is a vibration. So the atomic lattice vibrates. And if you cool that thing off really quickly, then the crystalline structure is not nice. It's very confused. So and that makes it unstable. So it will maybe break. So you want to make sure that you cool it down slow enough. And that's how simulated annealing also works. So every solution to a problem is associated with a certain temperature problem. And you decrease the temperature over time. So which just means So if we have a solution surface, I want to make big jumps on that solution surface. I start with a high temperature, but over time I decrease the temperature, and I want to make smaller and smaller um, jumps. So if you imagine you have a solution surface that looks like that, then you may be stuck in here, go down here. You want to make sure that the temperature parameter is high so that you can give a kick or get a kick and get over here. But over time, I want to make sure that my temperature becomes smaller. I don't want to be kicked out of that here because this is, it seems, at least in that equation, it seems my global minimum. So I don't want to be kicked out here. So the temperature parameter over time ideally decreases and the algorithm settles in a global minimum. So simulating annealing, it's in the algorithms community, we also very often call it the algorithm of the desperate because it will always converge. But if you look at, so the question is, when does it converge and how long does it take? With quantum annealing, you remember what we use here too is an effect. I think I mentioned that at the beginning. It's quantum tunneling. And again, if we look at that surface here, and let's say we start with our algorithm here, the smaller the integral over under that curve becomes, the more likely it is that my algorithm can just tunnel through here, and I don't need a kick here. It just tunnels through and will end up in the global minimum. Of course, I have to formulate my problem correctly because if I don't, then I may not be able to tunnel through my algorithm. So if this integral under the curve is too big, and too big depends on what the problem landscape looks like, then it will not be able to tunnel through. So quantum annealing specifically, again, we start with a Hamiltonian of t. So we have our final Hamiltonian here on the left, plus theta gamma of phi of a Hamiltonian for transverse field Hamiltonian that we see here. And here it's again significance of how important that Hamiltonian becomes over time is given by the transverse field coefficient gamma. This controls the traversability of the solution landscape, which is just the traversability, what I just mentioned here. So if we look at the d-wave system specifically and an Ising spin problem, an Ising spin problem is a mathematically equivalent problem to what the d-wave can solve. And then there's another one, it's called quadratic unconstrained binary optimization, or QUBO, which you may want to have a look at. It's a way of formulating that initial matrix that we supply to the system. The problem, how we supply it, right? And so what I give you an example here. So any quantum annealing system or any quantum computer in general, it's a graph. You have qubits, the nodes that you see here, and you have interaction terms, which is the edge that you see here in that picture. And if we solve that solution or solve that problem for -1, -1, you just execute the equation that I've given here, and the result will be 0.6. So you see the minimum value here comes with +1, -1, which is -1.2. Okay. And the algorithm, it incorporates two parts, which is the initial Hamiltonian and the problem Hamiltonian. Initial Hamiltonian, nothing new, it's the initialization that we learned about before, and the problem Hamiltonian that we see here. And the problem Hamiltonian you see on the left-hand side here with HIs, and the Z's, the Z matrices here, is the diagonal terms, and the JIJs and the I's and J's here in our Ising spin problem is the interaction terms between the single qubits. So if you have a matrix, then this sort of looks like I, J, I have I, J, then I may have with I and J an interaction term here, whatever that is, let's say 5. Okay, but it's generalized as to n qubits. Right now the d-wave has, or any d-wave system has 2,000 qubits. There are other things that we need to consider, like how many connections does each qubit have to each other qubit, which is limited to 6 right now, but with a new version we'll have more. Anyway, so this means if you look at that equation here, the matrix that you get is an upper triangular matrix. And it's constrained by an envelope function, as we said before. So the S is our time. So if A of S and B of S. And totally identical to the adiabatic quantum computing that we looked before, the initial Hamiltonian loses importance over time. And the system will remain in the ground state of all the instantaneous Hamiltonian pass through, provided the change is made sufficiently slowly, adiabatically. And here you see the envelope functions crossing each other. And at some point, B of S will become more important. Okay. And there's this landscape metaphor that I always use. It's how we walk the energy surface, so the surface of these problems. So with a gate model computer, remember, you solve your problems by applying gates. But here you walk as you have a representation of the solution space in terms of the energies that they have. You could say good solutions sit in the valleys and bad solutions on the hilltops. And what your algorithm can do, the classical one, and simulated annealing algorithm, it can walk this surface. You can parallelize. It can 1,000 times. You can use 1,000 CPU cores and then walk 1,000 times. But still, if you have billions of solutions, still sequential processing. And what annealing does is it starts at one point, but orients towards the algorithm. You can imagine it orients towards the minimum. And if everything is formulated correctly, flies through that solution landscape and ends up in the global minimum. That's how an annealing system solves a problem. Yeah, here another perspective on that, showing that thermal effects help systems explore complicated energy landscapes and find stable minima, which is the same can be achieved by quantum system. And the corresponding classical optimization problems, so remember we had the Hamiltonian, the initial Hamiltonian and the problem Hamiltonian on the right. In the Ising spin problem, the corresponding classical optimization problem below, because we only care about the right-hand side, right? The left-hand side is given by the system. The right-hand side is our problem that we encode. So we only have to encode this matrix. And this could mean, a good example is again traffic flow. Let's say vehicles use 3 routes. I have, let's say I have I have my chip that looks like that. I have maybe a block of other 8 qubits here, and so on. So I have the car number 1, which can take these 3 routes. Then I have the car number 2, which can take these 3 routes. It's different, but then it may happen that my car number 1 goes down that way and my car number 2 goes down that way. So at some point they have an overlap. And let's say it's this route for that one and this route for that one. Then I have to make an interaction term such that the more I have, maybe some more is coming from here, that the more interactions I have, that the more unlikely it is that this resulting qubit is set to 1 for car number 1 and set to 1 for car number 2 and many other cars. I want to have it set to 1 only for a limited number of vehicles, because the assumption here is the more vehicles I have meeting at the same road segment, the more likely it is that this is traffic jam, and this is what we want to avoid. So that's how you formulate a problem very easily. There is this very old slide already, because I know people are always skeptical about quantum annealing still. We use it, we solve many problems with it, and we have a couple of things in the pipeline that we will work on in the near and distant future. But there's this announcement that IBM made on December 7th, 2015, where they said quantum annealing systems are so simple and easy to implement. And then it was funny that a Google blog post came out on 8th of December, so 1 day later, where they showed that a quantum annealing system can potentially be 100 million times faster than a classical computer. So if you look at that closely, you will see some controversies in here. The question is always, how do I compare a quantum computer with a normal computer? There's a quantum annealing chip, like a gate model chip. It's a chip the size of your thumbnail. The big thing that you see around it is just a dilution refrigerator to keep it cool, because we work with superconductors most of the time. But how do you compare it? Is a reasonable and a valid comparison to take my quantum chip and compare it with one classical chip? Is my comparison my quantum chip and I compare it with the biggest data center that I have, or the most powerful supercomputer on Earth? It varies. So ideally, and that's the very interesting thing, this was a comparison made with a one classical chip. But the thing that we really want to do is take the most powerful supercomputer that we have on Earth, let that one try to solve a problem. If it can't, let's have a look at a quantum chip. Can it solve that problem? If it can, then you have quantum supremacy. And this is what happened last year. Google showed quantum supremacy with an artificial experiment, though, but still very valuable because it shows that with a quantum chip, you can be enormously faster than with a classical computer. There are different statements about this problem. You may Google quantum supremacy because one statement says that's provided by Google, the most powerful supercomputer on Earth would take 10,000 years to solve that problem. IBM says something else. They say it just takes minutes. There is this feud going on. I think it's a good scientific debate, and we will see more of this in the near future until someone really has the one quantum supremacy experiment that no one can even dispute or try to dispute because it's just obvious. Well, we don't have that yet. That is it for quantum computing. I hope you enjoyed the lecture. As always, so I posted some updates on Blackboard. And as always, if you have questions, please reach out to me via email. My VW email address is the one that I prefer. The other one is a very small mailbox, so it's always full. So please reach out to me at florian.neukert@vw.com. And what we can do is always we can schedule individual video sessions via Skype, Zoom, whatever you want or prefer. You can email me. We can try to solve everything and explain everything better that you don't understand or that you want to have more details on if I didn't explain well enough. And let me know. Sometimes I know I go over things rather quickly, so maybe if you feel there is more or better understanding that you need, then please reach out to me. I hope to see some of you next year at university, and I hope operations at university will at some point again resemble something that we can consider normal. We will see. Until then, good luck at the exam. If you have questions, reach out to me. Look at the updates on Blackboard. Thank you very much.